Hey there. Before we begin, take a moment to settle in. Dim the lights, take a deep breath, and let your mind begin to drift. Tonight, you're about to fall asleep to one of the most mysterious and mind-bending questions ever asked. Is time real? We live our lives by the clock, counting hours, aging, remembering the past and dreaming of the future. But what if all of that is just an illusion? In this bedtime science journey, we'll gently unravel what physicists and philosophers have discovered about time, how it flows, how it might not flow at all, and whether it even exists in the way we think it does. It's a story that spans Einstein, quantum mechanics, and the very edge of our understanding of reality, designed to help you relax, think deeply, and slowly drift into sleep. If you enjoy calm, thoughtful content like this, don't forget to like the video, subscribe to the channel, and hit that bell so you won't miss the next audio journey into the unknown. Now, close your eyes, let your thoughts float, and let's begin the question. Is time real? Time. We live by it, measure it, chase it, and often feel like we're running out of it. Clocks tick, days pass, and years accumulate like footprints behind us. But what if all of this, our sense of before and after, our memories of yesterday, our hopes for tomorrow, isn't what it seems? What if time, as we experience it, is not a fundamental feature of the universe, but a trick of the mind? In this chapter, we begin our journey with a simple, unsettling question. Is time real, or just an illusion? From the moment we wake up and glance at the clock, to the moment we fall asleep hoping for more hours in the day, our lives are ruled by time. It feels as solid as the ground beneath us. Yet the more closely we examine it, the more slippery it becomes. Our brain registers change, it links events together, it remembers, and through that, it constructs a timeline, a narrative. But that timeline may not reflect reality. It may just reflect how our minds keep us sane. Think about dreams. When you dream, entire stories play out. Sometimes they feel long, other times short, yet they often take place in just a few minutes of REM sleep. Your brain bends time, compresses it, stretches it, even loops it. It's a clue. Our internal experience of time is flexible, malleable, and in many cases completely disconnected from physical time. The philosopher Immanuel Kant argued centuries ago that time isn't something out there, it's a framework our mind uses to organize experiences, much like space. In other words, time may be a cognitive tool, not a cosmic one. Let's take this further. Neuroscience tells us that our sense of now is a construct. What you feel as this very moment is actually a stitched-together story your brain creates from different sensory inputs. Light hits your eyes, sound reaches your ears, sensations register on your skin. But none of these signals arrive at the same instant. Your brain delays your experience of the world just enough to synchronize them. So even your present is delayed. What you're experiencing is not the world as it is, but as it was a fraction of a second ago. That tiny lag is invisible to you, but it's always there. Now consider memory. We remember the past, but not the future. This gives us a direction to time. Yet memory is not a perfect record. It's a reconstruction, often flawed and malleable. Studies show how easily our memories can be rewritten, influenced, or even fabricated. So if our sense of the past is partly a lie, and our sense of the present is delayed, what is left of real time? Psychologically, time speeds up as we age. A summer at age 5 feels like forever. At 40, it slips by in the blink of an eye. There's no change in the physics of the world around us, only in how we process time internally. This raises a deep question. If time is not experienced equally by all minds, does it even exist outside the mind? Some cultures have radically different notions of time. In the Western world, time is linear, a straight road from the past to the future. But other cultures, like some indigenous American or Eastern traditions, view time as cyclical, or even fluid. Language reflects this. In Hopi, a Native American language, there's no direct equivalent of past, present, and future. Instead, events are described based on whether they are manifest or unmanifest. Again, our framework of time might be a product of culture, not nature. None of this proves that time isn't real, but it challenges the idea that our everyday experience of it is anything more than a constructed illusion. It might be the scaffolding for human consciousness, not a skeleton of the universe. In the next chapter, we'll leave behind the world of human perception and ask what physics, classical physics, has to say about time. Spoiler, for a long time, it seemed very real indeed. To truly understand time, we must travel back, not in time, but through the evolution of thought. Long before quantum fields and relativity shook the foundations of science, the universe was imagined as a vast ticking machine, perfectly ordered, measurable, and predictable. This was the world of classical physics, and in that world, time was not questioned. It was real, absolute, and as unchangeable as the laws that governed falling apples and circling planets. In the 17th century, Isaac Newton, a towering figure in the history of science, gave the modern world its first rigorous mathematical vision of how nature worked. His laws of motion and universal gravitation laid the foundation for centuries of scientific progress. Central to Newton's universe was the idea that time exists independently of anything else. He wrote that absolute, true, and mathematical time flows equably without relation to anything external. In other words, time was like a universal river flowing evenly everywhere in the cosmos, regardless of whether anything was there to see it, use it, or experience it. This notion of time as objective, constant, and completely detached from the contents of the universe made sense in Newton's deterministic world. In that framework, if you knew the exact position and velocity of every object in the universe and the forces acting upon them, you could calculate the future and the past with perfect precision. Time was simply the stage on which events occurred. It was the ruler with which you measured change, not the change itself. Time, to classical physics, was as real as space, mass, or energy. This idea carried immense power. It allowed for the precise prediction of celestial motions. With Newton's laws and his absolute time, astronomers could chart the orbit of planets, predict eclipses, and even send ships across the seas using accurate clocks. Time became a tool of civilization, a mechanical heartbeat of the universe, accessible to human instruments. But there's a curious thing about Newtonian time. It doesn't care about the direction of events. In classical physics, the equations work the same whether time moves forward or backward. This property is called time reversibility. For example, if you watch two billiard balls collide and reverse the video, the collision looks perfectly natural. Newton's laws do not have a built-in arrow of time, and yet we experience time in one direction. You remember yesterday, but not tomorrow. A cup falls and shatters. It doesn't reassemble and leap back into your hand. Heat flows from hot coffee into cold air. Never the reverse. This tension between the symmetric time of physics and the asymmetric time of experience will haunt science for centuries. But in Newton's era, it was largely ignored. Time, even if directionless in theory, was treated as moving steadily forward in practice. The Industrial Revolution, which emerged from this scientific worldview, amplified the importance of time as a measurable, uniform resource. Factories operated on schedules, railroads synchronized clocks across continents, time zones were invented. The tick of the clock became the rhythm of modern life, and Newton's version of time, the straight line stretching from past to future, fit perfectly into the world humans were building. Still, not everyone agreed. In the late 19th century, German philosopher Immanuel Kant proposed that time, like space, might not be something out there in the universe, but a feature of how human beings structure their experiences. He saw time as a kind of lens through which we view reality, not a part of reality itself. But science wasn't ready to hear that yet. The success of Newton's laws was overwhelming, and it seemed that the universe, from the stars in the sky to the gears in a watch, ticked along with absolute time. But cracks were forming beneath the surface. As scientists observed the behavior of light, electricity, and magnetism, they began to discover that the world might not be as absolute as Newton claimed. For instance, James Clerk Maxwell's equations of electromagnetism hinted at something strange. The speed of light seemed to be the same, no matter how fast you moved. This idea clashed with classical physics. If time and space were absolute, then different observers should measure different speeds for light depending on their motion. But they didn't. The 19th century ended in a state of growing tension between experiment and theory. The concept of ether, a mysterious substance thought to carry light waves, was disproven. Experiments like the Michelson-Morley test found no difference in the speed of light due to Earth's motion through space. Something was deeply wrong with the classical picture. And then, in 1905, a 26-year-old patent clerk named Albert Einstein proposed something radical. What if time wasn't absolute? What if time depended on your motion? What if Newton had been wrong? Not just about some technicality, but about the very nature of time itself. Einstein's theory of special relativity would redefine the very fabric of reality. Time would no longer be the same for everyone. The river would no longer flow at the same speed through all parts of the cosmos. Instead, time would bend, stretch, and twist depending on speed and gravity. The steady tick-tock of Newtonian time would dissolve into something far stranger. But before we move into Einstein's revolution, we must pause and reflect. Newtonian time served us well. It built the modern world, structured our industries, guided our machines. It taught us to think of time as something we could control, measure, and master. But as the 20th century dawned, science began to pull the rug out from under that certainty. Classical physics taught us that time was real, objective, and absolute. It gave us a vision of the universe as a predictable machine ticking in unison. But nature, it turns out, is more subtle. In the next chapter, we'll explore Einstein's strange world, a world where time runs faster or slower, depending on how you move, and where the idea of a universal now vanishes entirely. In the early 20th century, the foundations of physics trembled under the weight of new discoveries. Newton's world, the clockwork cosmos governed by absolute space and time, no longer matched the experimental evidence. Nature was revealing cracks in the smooth, predictable fabric that had governed scientific thought for over 2 centuries. And it was Albert Einstein who stepped into this chaos and reshaped the universe. Einstein's insight was as revolutionary as it was simple. What if time is not universal? What if each observer has their own version of time, ticking according to their own motion through space? In 1905, in his theory of special relativity, Einstein proposed that space and time are not separate, absolute entities. Instead, they are interwoven into a single fabric, space-time. And within that fabric, time is relative. Relative to what? To speed. According to Einstein, the faster you move through space, the slower you move through time, relative to someone at rest. This isn't a metaphor or a trick of perception. It's a measurable, real effect called time dilation. Imagine 2 twins. One remains on Earth. The other boards a spaceship that travels near the speed of light. For the traveler, the journey seems short, but when they return, they find that years or even decades have passed on Earth. The twin who stayed behind has aged far more than the one who traveled. This is not science fiction. It's been confirmed experimentally with fast-moving particles, atomic clocks on jets, and satellites in orbit. Time actually flows at different rates depending on your speed. This defies common sense. How can something as solid as time stretch and bend? It happens because of the nature of light. Einstein's theory begins with a bold postulate. The speed of light is constant for all observers, regardless of how fast they are moving. If you chase a beam of light, it doesn't appear to slow down. It still moves away from you at the same speed. To preserve this universal speed, something else must give way. That something is time. Let's break this down. Suppose you're in a spaceship traveling at an incredible speed. Inside the ship, you shine a flashlight straight up. From your perspective, the light travels vertically, but from the perspective of someone watching the ship from Earth, the light travels diagonally, since the ship is moving horizontally as the light moves up. For the light to take a longer diagonal path but still arrive at the same time, something must change. That something is the flow of time itself. Time for the traveler slows down so that the light can cover more distance without violating the speed limit of the universe. This realization upended centuries of belief. No longer was time a universal metronome. It became personal. Proper time, as it's now called, is the time measured by an observer's own clock, and that time is not necessarily the same for someone else moving at a different velocity. But Einstein didn't stop there. A few years later, in 1915, he released his theory of general relativity, which extended these ideas to include gravity. In this framework, gravity is not a force in the traditional sense. It's a warping of space-time caused by mass and energy. Massive objects like stars and planets bend the space-time around them. And just like motion affects time, so does gravity. The stronger the gravitational field, the slower time passes. Near a black hole, for example, time nearly grinds to a halt. Again, this isn't just theory. We've observed this effect with incredible precision. Atomic clocks on Earth's surface tick slightly slower than those on airplanes or satellites. Without correcting for these differences, the GPS system, relying on extremely precise timing, would drift by kilometers each day. So now we live in a universe where time is no longer flat. It stretches and contracts. It warps around massive bodies. It's different for each observer. In Einstein's cosmos, there is no universal now. There is no single moment that exists everywhere in the universe. Events that are simultaneous for one person may not be for another. This shatters another cornerstone of human experience, the idea of a shared present. In relativity, simultaneity is relative. If you and a friend are far apart, say light years away, and both flip a coin at what feels like the same time, another observer moving differently might disagree about which flip came first. Time loses its universal order. This leads us to the block universe interpretation, an idea that will take center stage in a later chapter, but the seed is already planted here. If all events in space-time exist, past, present, and future, then time doesn't flow. We merely experience slices of this block moment by moment. The future may already be there, waiting. Einstein himself hinted at this view. When a friend of his died, he wrote in a letter, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." A chilling thought, perhaps, but one rooted in the logic of relativity. Yet, for all its elegance, Einstein's time is still time. It may be relative, flexible, and affected by gravity, but it still plays a role in the equations. It still allows change, causality, progression. It doesn't erase time. It complicates it. And here's the paradox. Special and general relativity expanded our understanding of time immensely. They proved that time is not absolute. They showed that it bends and warps, and they revealed that now is subjective, but they also made time more physically real than ever before. Time became a dimension, just like length, width, and height. You can travel through it, albeit only in one direction, and you can measure its distortions. Still, these triumphs are not the end of the story, because even Einstein's space-time, brilliant as it is, starts to unravel when confronted with the strange world of quantum mechanics. When we peer into the tiniest scales of the universe, time once again slips from our grasp. In the quantum world, the notion of time becomes even stranger, and some physicists begin to wonder, does time even exist at all? In the next chapter, we dive into this deep uncertainty, where classical physics saw time as absolute, and relativity saw it as relative. Quantum mechanics offers something even more bizarre, a reality where time might be an emergent illusion, perhaps not fundamental at all. If Einstein bent time, quantum mechanics breaks it, or at least calls it into question in the most fundamental way. In the macroscopic world where apples fall and planets orbit, time has rhythm, it has consistency. But as we shrink down into the smallest scales of reality, into the strange probabilistic world of quantum particles, time begins to fade into something. Quantum mechanics, the most successful and precise theory in all of science, governs the behavior of particles smaller than atoms, electrons, photons, quarks. It describes a world that defies intuition, where particles exist in multiple states at once, only choosing a state when observed. And unlike relativity, which gave time its own dimension in the fabric of space-time. Quantum mechanics treats time in a bizarrely asymmetrical way. To understand the problem, we must start with the structure of quantum theory. The Schrödinger equation, the cornerstone of quantum mechanics, describes how a quantum system changes with time. But here's the catch. Time is not treated like space in this equation. It is an external parameter, something imposed from the outside, not something the system contains. In other words, quantum mechanics relies on time to work, but it never explains what time is. This is strange. In relativity, time is dynamic. It bends and warps. It is affected by gravity and motion. In quantum mechanics, time is just there, unchanging and absolute. That's a problem, because when we try to unify quantum mechanics with general relativity to create a theory of quantum gravity, we run into a contradiction. One theory treats time as an actor, the other treats it as a backdrop. These two views cannot both be right. And it gets weirder. In the quantum world, the future is not determined. A particle might be here, or it might be there. It might spin this way or that. It exists in a superposition, a blend of possibilities, until a measurement is made. The act of observing collapses the wave function into a specific outcome. But when exactly does this collapse happen, and why? These are still open questions. Take the famous double slit experiment. Fire a single electron at a barrier with two slits. If unobserved, it acts like a wave, interfering with itself, suggesting it went through both slits at once. But the moment we observe which slit it goes through, it behaves like a particle. The wave vanishes, the superposition ends, and we get a definite path. Observation changes reality. But does it also change time? Some interpretations suggest it does. In retrocausality models, measurements made in the present can influence outcomes in the past. That sounds absurd, but in quantum mechanics, absurdity is almost normal. There are experiments where a decision made now seems to affect how a particle behaved earlier. The logic of cause and effect, something time supposedly protects, starts to unravel. So does time flow at all in the quantum world? Here's where things get radical. Some physicists propose that time doesn't exist at the fundamental level. It's not a thing that flows or ticks. It's an emergent property, like temperature. Think of temperature. No single atom has a temperature. Temperature only arises when you have a collection of atoms. In the same way, time might arise from a system of interacting quantum bits. It might be something that appears when enough information is processed, like a narrative constructed by a computer. This is the view in quantum cosmology. If you treat the entire universe as one quantum system, it has no outside observer. That means the wave function of the universe doesn't evolve in time. The equations describing the entire universe suggest a timeless state. This leads to the Wheeler-DeWitt equation, a quantum version of Einstein's equations that lacks any time variable at all. The universe just is. No past, no future. Just an infinite now. But we clearly experience time. We grow older. Stars are born and die. So where does this feeling of time come from? Some theories suggest that time emerges from entanglement, the strange quantum connection between particles. As systems become more entangled, information flows between them in complex ways. That flow, that increasing complexity, may be what we interpret as time. In this view, time is not fundamental. It is statistical. It's what you get when you zoom out and watch the dance of probabilities become patterns. Another approach comes from loop quantum gravity, a leading attempt to unify relativity and quantum mechanics. In this framework, space and time are made of discrete units, tiny loops of quantum information. Time is not continuous, it is granular. Between two moments, there is not an infinite series of in-between instants. There are jumps, gaps, a finite number of steps. If true, this would mean that the flow of time is not smooth at all, it's digital. And yet, our experience is smooth. We feel time flowing like water, but that feeling may be an illusion created by our brains. Neuroscientists have found that the brain doesn't process time in a straightforward way. It builds it, constructs it, It stitches together sensory information into a coherent sequence. That coherence might be nothing more than a clever trick of biology. The Page-Wouters mechanism, proposed in the 1980s, explores this even further. It shows that, under certain quantum conditions, a static system, one with no external time, can still contain internal subsystems that experience change. In other words, a timeless universe can give rise to observers who experience time. We are part of that subsystem. We experience what feels like a flow, but the larger whole doesn't change. All of this leads to a breathtaking, unsettling conclusion. Time, as we know it, may be a user illusion, a tool the brain uses, a pattern that emerges, a story stitched from correlations. Even causality, the sacred chain of cause and effect, starts to wobble. Quantum experiments like delayed choice quantum erasers and entangled particles show that effects can appear to precede causes. That's not to say we can send information to the past, but it challenges the very idea of a fixed timeline. So what are we left with? A reality where time is not fundamental, where the flow of time may be an emergent property of consciousness or entropy, where the basic equations of the universe don't even require time to exist, where the past and future are not separate places, but interwoven features of an underlying timeless structure. And yet we age. We remember, we hope, we plan, we live inside time. This contradiction is not just a scientific problem. It is a human one. We are creatures of time, wired to fear its passage, to long for the past, and to dream of the future. The possibility that time is an illusion doesn't make its effects less real. We still suffer, we still lose, we still run out of time. But perhaps understanding time as emergent, not eternal, can liberate us. If the universe doesn't flow, and only we do, then maybe time is a song we sing, not a drum we follow. In the next chapter, we dive into the philosophical storm that erupts when science begins to say what many philosophers suspected all along that time, and everything about it may be nothing more than an illusion. If time is an illusion, or at least not fundamental, why does it feel so real? Why do we remember the past, but not the future? Why do we grow older, not younger? Why do eggs break, but never unbreak? And why does a cup of hot tea cool down, but never heat itself back up? These questions lead us to a concept that, despite all the strangeness in physics, remains undeniably central to our experience: the arrow of time. While physical laws from Newton's mechanics to quantum equations are mostly time-symmetric, meaning they work the same if you run them forward or backward, our lives are anything but. There is a clear direction to time in our world. Something pushes the present into the past. That direction is what we call the arrow. But where does it come from? To begin understanding the arrow of time, we must meet a ghost that haunts every conversation about time: entropy. Introduced in the 19th century as part of thermodynamics, entropy is often described as disorder, but it's more accurate to call it a measure of the number of ways a system can be arranged. A low entropy state is ordered, predictable, structured. A high entropy state is messy, chaotic, randomized. Now here's the key. The second law of thermodynamics states that entropy in a closed system tends to increase over time. It's not a rule of logic or geometry. It's a statistical trend, rooted in probability. A tidy room has fewer possible configurations than a messy one. So if you shake the system, even gently, it's far more likely to end up in a mess than to spontaneously clean itself. And so entropy increases. Time moves forward. We age. Stars burn out. Universes cool down. This increase in entropy is the thermodynamic arrow of time, and it may be the most fundamental explanation for the direction of time we experience. It underlies everything from the melting of ice to the memory in your brain. Every process you can think of that marks a before and after is governed, directly or indirectly, by entropy. But here's the puzzle. If the laws of physics are reversible, why is entropy always increasing? The answer, strange as it may sound, may lie in initial conditions. That is, the arrow of time exists because the universe began in an extremely low entropy state. At the Big Bang, The universe was hot, dense, and despite that chaotic description, highly ordered in terms of gravitational potential. There were few clumps, few structures, entropy was low. Since then, the universe has expanded and cooled, and entropy has risen by galaxies, stars, black holes, and life itself. The arrow of time is not baked into the laws of physics. It's inherited from the universe's birth. But why was the universe born in a low entropy state? No one knows for sure. Some physicists suggest it's a cosmic accident. Others argue that the laws of gravity and quantum mechanics conspired to make such a beginning likely. Still others propose that we're living in a branch of the multiverse, where low entropy beginnings simply allow for conscious observers like us to exist, a variation of the anthropic principle. In any case, it means something extraordinary. The future is not more uncertain than the past because of physics. It's because we are moving away from a unique, improbably ordered moment in cosmic history. That brings us to another key arrow, the psychological arrow of time. We remember the past. We don't remember the future. This asymmetry is so deeply embedded in consciousness that we often confuse it with time itself. But from a physics standpoint, it's curious. Your brain is just a physical system, governed by reversible laws. So why do memories accumulate in only one direction? One answer, again, ties to entropy. Memory formation requires information storage. It requires change in a physical system. And such change is only sustainable when energy flows from high to low. When entropy increases, your memories are entropy markers. They reflect changes in a brain shaped by irreversible thermodynamic processes. So our psychology may simply be riding the same current that drives the physical arrow of time. There's also the causal arrow of time, the idea that causes precede effects, that we act before results are felt, that we strike the match before the flame appears. But this too may arise from entropy. In a low entropy past, fewer causes exist. As time unfolds and entropy rises, outcomes become more complex. The arrow of cause and effect flows along the same path. And yet, quantum mechanics complicates all of this. In some interpretations, like the many worlds interpretation, every possible outcome of every quantum event actually occurs, branching into separate parallel universes. In such a scenario, time is not a straight line, but an expanding tree of possibility. The arrow of time is not a simple road, but a divergence, a fractal pattern in Hilbert space. Other interpretations, like retrocausal models, allow for effects to influence causes, at least statistically. These ideas remain speculative, but show how fragile our concept of temporal direction becomes at the quantum scale. Still, entropy remains the most solid ground. It's measurable, it's predictive, it's woven into the cosmic fabric. Even black holes, once thought to be pure voids, obey the second law. According to Stephen Hawking, black holes have entropy, they radiate heat, they evaporate. Time, even at the edges of reality, has an arrow. But there's a twist. In some cosmological models, the universe doesn't just expand forever. It may someday contract. If that happens, entropy might start to decrease. Could time reverse? Would broken glasses leap off the floor and reassemble? Would we live our lives backward, unremembering everything? Some theories suggest no. The arrow is tied not to motion but to structure. Others say yes. Entropy controls everything. And if it reverses, so will time. Still others propose something truly exotic, that the universe is time-symmetric, with two time arrows pointing away from the Big Bang in opposite directions. In this view, there's another version of us on the other side of the Big Bang, living their lives in reverse, as far as we're concerned. These speculations are wild, but they arise from serious physics. Yet for all these layers, the thermodynamic, the psychological, the cosmological, there remains a truth. The arrow of time gives our lives meaning. Without it, there is no change, no death, no birth, no evolution, no memory, no choice. If time didn't have an arrow, you would be as likely to see your grandfather walk backward out of a grave as to see your child born. The arrow gives us purpose, direction, identity. It defines everything we know. But if that arrow is not fundamental, if it is emergent, statistical, or contingent, what does that say about our meaning, our memories, ourselves? In the next chapter, we move from physics to philosophy, where these questions have long simmered. There we'll explore whether time exists outside the mind, or if it is, ultimately, a construction of consciousness. Imagine stepping outside of time, not just watching it pass, but truly stepping beyond it, like standing on a mountaintop where past, present, and future are laid out in front of you all at once. This is not science fiction. It's a real and serious idea in modern physics. It's called the block universe, and it challenges everything we intuitively believe about the nature of time. In our everyday experience, time flows. We wake up, eat, breathe, think, and move through a sequence of moments. The past is fixed, the future is unwritten, and the present is a constantly vanishing instant. But what if this feeling is an illusion? What if the past, present, and future all exist simultaneously, unchanging, eternal, and equally real? This is the vision of the block universe, also called the eternalist or four-dimensionalist perspective. It arises directly from Einstein's theory of relativity. In special relativity, there is no absolute now. Two observers moving at different speeds can disagree on whether two events happened at the same time. What is now for you might be past for someone else, and future for another. This destroys the idea of a universal present moment. So what's left? Instead of a three-dimensional world moving through time, relativity gives us a four-dimensional space-time, a single entity where time is treated as just another dimension, like height, width, or depth. Events are not happening, they are. They occupy fixed positions in this four-dimensional structure. In this model, the universe is a block where every event from the birth of stars to your last breath is already there, like cities marked on a map. You as a person are a long worm-like structure stretched through time. Your baby self at one point, your adult self at another. You don't move through time. Your consciousness merely experiences one slice at a time. There is no objective now. No past has vanished. No future is yet to be. Everything exists, unchanging and complete. To many, this idea is deeply unsettling. It seems to strip us of free will. If the future already exists, are our choices real? If time doesn't flow, is anything truly happening? But the block universe has strong support in physics. General relativity, which extends Einstein's ideas to include gravity and acceleration, reinforces this timeless view. The Einstein field equations describe the structure of space-time, not how it evolves, but how it is. The equations don't tick. They describe the geometry of the universe all at once. This is timeless physics. Instead of equations that say this happens, then this, we have equations that describe a relationship between all events, past and future, in one grand geometry. Nothing is in motion. Everything just is. Quantum mechanics seems at odds with this, especially because it introduces probabilities and changes. But even here, some interpretations, especially those aiming to unify quantum physics and gravity, are pushing toward timelessness. One of the most striking is the Wheeler-DeWitt equation, which we briefly encountered earlier. This is a proposed quantum theory of gravity, one that applies to the entire universe. And curiously, it has no time variable. None. The equation doesn't evolve. It doesn't describe change. It just is. A static description of the entire universe. So how do we get time from timeless physics? Some physicists propose that what we perceive as change is actually an emergent phenomenon. Time might arise from entanglement or from internal subsystems correlating with one another. In this view, the flow of time is a byproduct of limited perspective, like watching a movie frame by frame and mistaking it for motion. We don't perceive the block universe. We experience local slices of it, one by one. This experience gives rise to our feeling of now. But now is a subjective illusion. A traveler moving at a different speed sees a different now. The only consistent picture is that of the whole block, timeless, unmoving, complete. Some philosophers, like Hermann Minkowski, who first described space-time in mathematical form, embraced this view fully. He said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." But not all physicists are comfortable with this. The block universe conflicts with our experience of becoming, of time's passage. It seems to freeze history and deny change. Some argue for alternative models, such as presentism, where only the present exists, or growing block theory, where the past and present are real, but the future is not. These are philosophical positions, but they're informed by physics, and they raise deep questions. If the future exists, are we simply playing out a script? Can we meaningfully talk about choice in a block where everything already exists? Is time travel possible if past and future locations are real? And most unsettling of all, if we are just frozen 4D structures in space-time, what is consciousness? Some theories suggest our minds are climbing the time axis. Others claim we're simply snapshots of a larger pattern. But no explanation fully resolves the paradox. Yet the block universe has one undeniable strength. It matches the math, relativity, quantum gravity, and even some interpretations of quantum mechanics seem to support the idea that time is not fundamental, that change is not real in the ultimate sense. Instead, reality may be a fixed, eternal mosaic, and we are embedded within it, experiencing change because we are constructed to do so. But then, why do we feel the flow of time? Why do we yearn for the past, fear the future, and live so fiercely in the now? That may be a question not for physics, but for consciousness, for brains, for how information is processed, remembered, and imagined. The next chapter will tackle that mystery, how the illusion of time arises in the mind, and why even a timeless universe still feels like it's in motion, what if everything we think we know about the past, the future, aging, memory, change, is built on a fundamental misunderstanding? What if time, the invisible stage on which all of existence appears to unfold, is not real? This isn't a question reserved for poets or mystics. Some of the most advanced theories in modern physics are beginning to suggest just that time may not be fundamental, that it might emerge from something deeper or not exist at all, that what we call time is simply a way of interpreting the relationships between states of matter and energy, or between bits of quantum information. The idea is staggering. Time is so central to our lives, to our language, to our thoughts. We wake up, move through the day, age, anticipate. Our minds are anchored in time. The concept of a universe without time seems nonsensical. And yet, this is where science is leading us. Let's take a moment to understand what it would mean for time to not be real. It doesn't mean nothing exists. It means that change, as we perceive it, might be an illusion. That sequence, flow, and causation, the very building blocks of experience, are artifacts of a particular way of organizing information. We experience them as real, just as we experience color as real, even though color is not a property of objects, but of our perception of light. Several theories support this radical notion. One is loop quantum gravity, which attempts to unite quantum mechanics and general relativity. In this model, space and time are quantized, broken into tiny, indivisible chunks. But when researchers attempt to write the equations describing how the universe evolves in this theory, something strange happens. Time disappears. The fundamental equation describing the whole universe is timeless. Similarly, in the Wheeler-DeWitt equation, which attempts to describe the entire universe as a quantum system, there is no variable for time. The universe just is. Physicist Carlo Rovelli, one of the leading proponents of loop quantum gravity, argues that time is not part of the fundamental layer of reality. Instead, it emerges from relationships between subsystems. Imagine you are inside a watch. You can feel the gears turning, and from that motion, you deduce time. But step outside the system, and you see all the gears as a single object, frozen in a larger context. Time doesn't exist outside the motion of the gears. So too, perhaps, with the universe. Another path to timelessness is through entanglement. Some researchers propose that what we perceive as time is really the result of how quantum systems interact and become entangled. In this view, time is a property that emerges when certain subsystems observe others. From inside a system, it appears that things evolve, but from a more complete perspective, outside the system, everything simply is. This brings us to a strange implication. Time may be a feature of incomplete knowledge. When we know only part of a system, it looks like change is happening, but from a God's eye view, there's no change, just relationships. If true, this would mean that time is like temperature. At the level of individual particles, there's no such thing as hot or cold, just motion. Temperature is a macroscopic statistical phenomenon. Likewise, time might be a macroscopic illusion, emerging from a fundamentally timeless reality. Even consciousness doesn't escape this challenge. Neuroscientists have shown that the brain processes events in ways that make the illusion of time feel continuous. Our memories are layered, our attention has a lag. We stitch together frames of information like a flipbook. The sense of a now is constructed by the brain. If that mechanism were altered, our experience of time would change or even vanish. This invites a wild possibility. Our minds generate time as part of an evolutionary trick, a way to survive, plan, adapt, to organize an incomprehensible world into manageable pieces. Time might be a narrative, not a dimension. But if time is not real, what does that mean for everything built on it? What about causality? The idea that one thing leads to another. Some physicists believe that causality is more fundamental than time, that you don't need a timeline for one thing to influence another. Instead, information is the key. What matters is not when something happens, but what depends on what. Time is just a way to order those dependencies. This leads to a radical concept, that the universe may be better described by networks of events, not stretched across a timeline, but connected by causal relationships. These webs of cause and effect don't require time, they define it. And what about free will? If time isn't real, are our choices real? This is deeply philosophical. If every event, past, present, and future, is equally real in a block universe, then the future is already written. But if time is emergent, then choice itself might be a function of entangled systems, processing information. In other words, free will might still be meaningful within the illusion of time, even if time is not fundamental. So how do we live in a timeless universe? Surprisingly, it may not change much. Even if time is not real in the fundamental sense, it works. Our clocks still tick, our memories still accumulate, entropy still increases. These emergent patterns are so consistent and so powerful that they give rise to the world we know, but they may not last. In some models, entropy will eventually reach a maximum and no more change will be possible. The universe will become static. No heat, no light, no thought. Time, as we know it, will end. Not in fire, but in stillness. This moment is called the heat death of the universe. And it marks not just the end of stars and galaxies, but perhaps the end of the illusion of time itself. In that far future, the universe will be a frozen block of possibility, timeless and eternal. And yet, within that block, right now, you are here, listening, thinking, wondering. That's the paradox. Time may not be real, but the experience of time is, and perhaps in the end, that's all that matters.